Thanks for the invitation, and I'm happy to present the recent work on quantum state preparation and we get optimal T-count. This is a joint work with David Gossett and Robin Kosari. I'm from UC Berkeley, and this was done during my summer internship in Google. Right, and although this title doesn't seem to suggest anything about Boolean functions, there are actually something inside. Otherwise, I won't be working on it. I still see myself like a classical guy. Okay, so I will talk about the background and motivation first. It involves some like Clifford plus T circuit and what is T count and what is the problem of state preparation. And then I will mention our results. And I will start with a summary with talking about related open problems that I hope maybe you will like. And finally, if there are time, I wish I don't, I will talk about proofs. Okay, so please ask questions. Otherwise, I will need to talk about proofs. Okay, so what is Clifford? Clifford gates are some quantum gates that are defined by like Daniel Goldman in terms of quantum error correction. And these gates turns out to be useful there and many other things. So we have three special gates. The Hadamard gate, which is just computing the Fourier transform of a single qubit. And the phase gate, just putting a phase I on the cat1 state. And the C0. This is why it doesn't show. I think yeah, it doesn't, why it's truncated.
Do you have Firefox?
Yeah. Yeah.
I find Firefox's full screen PDF is like much better.
It's not too bad.
Probably if you download it and just present it with a Robin.
Yeah, let's see, maybe this one. Okay, this is better. At least it's not truncated. Okay, so we also have C0 gate. This is more like classical gate that performs linear transformation of the base state. And even with these three special cases, we have some non-trivial quantum phenomena here. For example, we can construct a Bell state that captures quantum entanglement, and we can do something like do this Fourier transform over hypercube faster than classical. So classical you need n log n time, but quantum you just need one layer. So this is cheap. So given this, well, the quantum circuit is just a bunch of gates that are from Hadamard or the phase or the C0. And we would wonder, okay, since it captures some quantum phenomena, is this sufficient for our purpose? It turns out not. So if you only have Clifford gates, it cannot represent all the quantum computation. And also more like sadly, due to this Gauss-Mann-Knell theorem, actually these circuits will be classically simulatable. So if you only have this, you'd better use a classical algorithm. So how to fix this? First, we want to be able to do all the quantum computation. And to do this, we just included one extra gate called T-gate. So T-gate is just the square root of the phase. So it's something special. And surprisingly, after adding this, it becomes universal. So it can encode all the quantum computation. Like all the BQP quantum algorithm can be written in this circuit form. And also we have a generalized Gauss-Mann-Knell theorem saying the classical simulation time will be still polynomial in the size of the circuit, but exponential in the number of T-gates you use. Okay. So a general goal in quantum circuit synthesis regarding this special Clifford plus T circuit is to reduce the T count, that is the number of T gates. Why this is interesting or important? First, due to classical simulation, as we saw in the previous slide, if you have small number of T gates, then you can use this Gauss-Mann-Knell theorem to have a faster classical simulation. So if you don't have a quantum computer, don't worry, you can still simulate it. And the second is about physical implementation. It turns out that fault-tolerant implementation for T-gates is more costly than Clifford gates. So if you want to build a quantum computer with some like architecture, and you put T gates in it and Clifford gates in it, and T gates will cost you more money. And third is about magic. So magic is quantifies like how much non-Cliffordness do you need to perform your whatever computational tasks. And this name magic is not what I invented, it's actually what they call. So it turns out there is a whole workshop that study magic. And these are the topics, like you see magic everywhere. And this partly motivates my, like why I'm interested, because I think, magician looks better than mathematician. This is what we do, and this is what they do. If I can choose, I would replace bracket with the racket, like a rabbit, and maybe change Grover to the flower. So doing this project makes me feel better. Okay, so the next thing is about state preparation. Like, what is the problem that we want to study? The problem is you are given an n-qubit quantum states explicitly, and you want to encode it in a quantum circuit with these Clifford plus T gates. And how many T gates do we need to construct it within this epsilon arrow in L2 distance, or like fidelity or other measures you want? This problem is useful for like various quantum algorithms and quantum communication and metrology and experiments. You want to construct a quantum state. More formally, this will be the process. We start with all zeros, and the blue lines are the qubits we care about, and the red lines are the ancillary qubits that we incorporate to facilitate our construction. And then we apply a bunch of gates. So there are H gates, single gate, phase gates, and T gates. And T gates, the number of those are the things we care about. And after this circuit, the first blue wires should output somewhat close to your target. And the ancillary qubits should be restored to all zero. So you can use it for other computation afterwards. So this is our task. And now, and then I will talk about the result. Is there any question regarding this problem setup?
In what metric we compute the error?
L2 distance. Okay.
And we allow measurements, right? Or no measurements?
So in our algorithms, we don't need measurements.
Okay.
For lower bounds, we can allow measurements. Okay, so those are the setups, and I will talk about the results. So for a single qubit case, so you are given a description of the single qubit, and how many T gates do you need to construct within epsilon arrow. So first, there is a very nice result, like a very general result by Solovay-Kitov, which shows you can do some polylog 1 epsilon. So this log like 3.97. This is very general. And it turns out, by a beautiful line of work, this has been improved to log 1 epsilon. And they use some algebraic number theory to study like Hadamard and T gates, how they interact. And also, there are some recent work showing this log 1 epsilon is necessary, and the proof is based on granularity. And also, this upper bound that does not need measurements, and the lower bound you allow measurements. Like even if you do measurements, you still need log 1 epsilon many T gates.
Granularity in what sense?
Like you want to approximate within like between epsilon or 10 epsilon, and then you must have like log 1 epsilon many bits to do that. Okay. So what about the general case? So imagine you have an n-qubit quantum state. How do we construct it? Let's fix the error to be constant for simplicity for now. So first, we can do something naive, okay? Because we know how to approximate each single qubit gate. Then let's just decompose your quantum state like preparing your quantum state with single qubit and CNOT gates. This is also like universal. So for every quantum state, you can just use 2 to the n many single qubit gates and also CNOT gates. You can construct it. And then for every single qubit gate, you use the previous result. You can approximate it with Clifford plus T. And then this will give you this upper bound. You have 2 to the n many gates, and each one of them will incur like nt gates because you want inverse exponential error to union bound. So this is a simple upper bound. Okay. Does this make sense to you? So this is the fork law. And surprisingly, you can get a square root saving roughly. So this is a work by Kliuchnikov and Schaeffer 4 years ago. Actually, you only need square root 2 to the n times n log n many t gates to do this. And they also provide a lower bound that matches this square root behavior after polynomials. Okay. And what's our result? We shave those polynomials. Yeah. So the major term is still going to be square root 2 to the n, but we don't have actual like n or log n there. And this is tight because of their lower bound. And in terms of the full spectrum, like for n-qubit and epsilon error, what we get, in their paper, they have this slightly more complicated form. You have like square root 2 to the n times n log n over epsilon. This is usually the major term because we think of n as like 2 to the n is much bigger. And you also have some additive term log square n over epsilon. And this will be dominant if like epsilon is extremely small compared with n. So these two bounds are incomparable, so you need to add them up. And they prove a lower bound that has square root 2 to the n log or epsilon. And because you have this square root, the previous single qubit case is incomparable to this lower bound. For example, when you put n equals 1 there, that lower bound only gives square root log or epsilon. But actually, we have this lower bound log or epsilon. So these two bounds are both necessary to describe the whole lower bound. And our result is to combine them in the upper bound sense. So we show that the upper bound can be improved to match the lower bound. So we have the square root to the n log or epsilon plus log or epsilon. Okay, so this is the main result of our work. And interesting, we have some byproducts from our analysis. And I personally find it more interesting than the main result. So we also answer the question for unitary synthesis for this special case of diagonal unitary. So you are given a unitary, the full description, and it's diagonal, so it's described by the diagonal entries. And you want to construct it as a quantum circuit using Clifford plus T gates. How many T gates do you need to make it epsilon closed? And this appeared in prior state preparation works as a key component. Like you want to somehow build a diagonal unitary. And also, because if you can do this, then sometimes it will be easy if you assume the target state has non-negative amplitudes, so that you don't work with complex numbers. If you have this, then you can ignore, like you can correct all the phases in the state, and you are working with literally the distribution. So it's a distribution state instead of some arbitrary quantum state. So this could be helpful. And also there are some interesting applications for this I will talk about. And for this problem, we show that the complexity of the number of T gates is the same. So it's also square root 2 to the n log or epsilon plus log or epsilon. So this is the same complexity for the state preparation problem. And as I mentioned, the upper bound doesn't use measurements, and the lower bound works for measurements. And you can have measurement and classical controlled flip-flop.
So all these results, do they also work if you have like CCZ gates?
You mean upper bound or lower bound?
I want to say upper bound first. Like, I mean, that's also a non-Clifford gate which gives you universality. So do the upper bounds also like?
I think so, because you can convert CCD data with some Clifford and you can produce tickets, right? So that every ticket can be replaced by a constant number of CCD.
Oh, so it's the constant number, okay.
Yeah, the constant will be hidden in.
Yeah, okay, sure.
And the error doesn't explode.
Yeah, because that replacement is like exact. So there is no error in that.
And then so because the generalized Gottesman-Grill theorem says you do it in time 2 to the t, right?
Yeah, so this doesn't show BQP equals P.
But even so, this would be doubly exponential.
Yes, if you use this very generic way, then certainly it will be double exponential. Yes,
So
that's crazy.
It's not an effective way.
Yeah, that's not effectively. Right. Okay, so this is the T count for diagonal unitary. And what are the interesting stuff I mentioned? So this is an application called batch synthesis. Imagine you have a bunch of single-qubit unitaries, U1, U2 up to UM, and your goal is to implement all of them. So here is the circuit. Like on the first wire, you apply U1, second wire, apply U2, and up to like the mth wire. So this is a depth 1 circuit. And what will be the T count necessary? So the natural attempt is to do it separately. Okay, so for the U1, we use the single-qubit synthesis result, and the U2, same for it. And to apply a union bound, we need to make sure each one of them will have errors smaller than epsilon over m. And this will have a T count m times log m over epsilon, because you have m of them, and each one will need log. And what we show is, if m is not too large, but still super constant with respect to epsilon, then you don't need to pay that. The cost will still be log or epsilon. So if m is small as log or epsilon, then you can implement all of them with the cost of log or epsilon. And recall that this log or epsilon is necessary even if you only implement one. So in other words, with the cost of implementing one, you can implement more. And if you compare, like you said, m to be this number, then the naive approach will incur an extra log factor.
Okay. Sorry, if you plug in m equal to log 1 over epsilon, don't you get log 1 over epsilon there?
Yeah, there is some arithmetic mistake.
You mean this here? Like this one, like this.
Yeah, shouldn't that already be log 1 over epsilon if you plug in m equal to?
Yeah, I mean, if m is log, then the main part is log, not just log.
Yeah.
No, this is smaller than this. So m is log, and the second term is log.
No, m is log, the next one is log. Ah, yeah, sorry, you're
It's
right.
over epsilon. So,
you're right.
so this m
Yeah,
over
yeah,
epsilon.
it's okay.
Oh, I see, okay, good.
Yeah. Okay, the next test. Okay, cool. So this is called batch synthesis, where you aim to implement different single-qubit unitaries. And it's natural to ask, what if I just want them to be the same? So this, actually, okay. And it turns out I will show that this one can be improved. But before that, let me actually prove to you why this is true. This is actually to be simple to be proved in just one slide. So recall our goal is to set m to be log or epsilon, and to show that you only need log or epsilon many t gates to do that. So this is a circuit that's our target. And you can use standard like diagonalization trick. For example, you can use Euler's angle theorem, so that every single qubit unitary can be written as diagonal unitary times Hausdorff gate times diagonal unitary times Hausdorff gate and another diagonal unitary. So this is something that's standard very standard in the literature. And then because of this decomposition, we can write the circuit equivalently into this depth 5 circuit. So we have A, H, B, H, C for every line. And also all these A's, B's, and C's are diagonal unitary. And we just need to implement them because Hadamard gate is contained as Clifford gate. So let's take a look at this, for example, for C. So C1 tensor C2 tensor up to Cm is a tensor product of single qubit diagonal unitary. So itself is going to be diagonal. And also it's going to be a diagonal unitary on m qubits. And we know what's the T count for that. So for m qubit diagonal unitary, the T count is square root 2 to the m log epsilon plus log epsilon. And then because m is log, so this on the square root is going to be log times log, which is log square, and taking square root is log. So this whole thing is order log epsilon. Right. So this is a very simple direct proof, and as I mentioned, this log epsilon is tight because you even need it to just implement one of them. But it's not clear, and this is an open problem, it's not clear whether this log is it's the best you can do. Because I would suspect not, because this argument is so simple. It doesn't really use any structure about this is a tensor product. In fact, we can implement all the diagonal unitary that is not a tensor product structure.
Yeah, I was going to ask even further, like it's common that we want to prepare many copies of the same state if all the AIs are equal.
We get tight bound. That's in the next slide.
Okay.
This, the whole math here is trying to deal with different diagonal unitaries. And for that, we don't know how to use the fact that it's tensor product, aside from just black box using this fact. But still, it's already something non-trivial that you can save some log terms from your naive approach. Okay, so this is the proof for the batch synthesis case. And the second is going to be about mass production that you already asked. So what if I want to implement the same unitary many times on the same on different wires? So we have a fixed single qubit unitary U, and we want to implement it on m wires. And what is the T count for it? And to compare, the batch synthesis implements different things, and here is the same. So we show that the T count is m plus log epsilon, and this is tight. So the log epsilon is necessary even for m equals 1, and this additive m term is necessary if the U itself is a T gate. Like you cannot generically compress the number of T gates. Okay. And if you compare, let's assume we have a unit cost, like we have a unit budget about T gates, that is log epsilon. So with this many T gates, we can use batch synthesis to get log epsilon many different single qubit gates. And using this mass production results, we can improve the log to log. But I want to mention that it's not clear whether this log can be strengthened into log even in this batch synthesis case. If it's true, then it will unify these two. Okay, and this mass production is somewhat looks like direct sum or direct product phenomenon in classical computational complexity, where you have a cost for computing one function, and what is the cost for implementing computing this function many times. And there are cases this scales linearly with the cost. There are cases these are not, and this is somewhat like that. So we also show it doesn't really multiply with the number of copies. Okay. And now I will also give you a short proof within one page about this fact. So as before, we can use Euler-Angle theorem, and we can assume this unitary U is just diagonal. Well, if it's diagonal, then ignoring the global phase, it's just 1 and e to the I theta on the diagonal. So now let's take a look at what's its behavior on my input state. So let's assume X is some computational basis state, and we apply U tensor M on it, and you will find that it actually just adds a global phase. The phase will be e to the I theta times hx, where hx is timing weight. You just count how many ones, and then you rotate e to the I theta many times of it. So this gives rise to the following simple circuit. You start from the input x, you compute in a classical way what's the Hamming weight. And then you look at just on the Hamming weight, you put the correct phase. And then you uncompute the Hamming weight. And this will give what you want. So the first step is a classical thing, that's just computing the Hamming weight. And you can do it with order n classical time complexity. So this is linear number of T gates. It's actually linear number of gates. It's not just T gates. You count like Clifford gates. It's also linear. And the third step is uncompute, and it's the same as the first procedure. So it's the same order n T gates. And the middle case is a diagonal unitary because you only look at this second register. And the diagonal unitary will act on this C equals log m digits. And we know what's the cost to implement it. So that if you plug C equals log m here, it will be square root m log 1 epsilon plus additive log 1 epsilon. And then by a and gm, square root ab is at most a plus b. We have m plus log 1 epsilon. That's it. Very simple proof. So these two are coming from this T count, optimal T count for diagonal unitary. Okay, so these are the results I want to talk about, and let me just summarize here and give open problems. So we show optimal T count complexity for state preparation task and a diagonal unitary synthesis task. And the bound is like square root 2 to the n log 1 epsilon plus log 1 epsilon. So the major term is going to be a square root saving. And for batch synthesis, we show that if you only want to implement log 1 epsilon many single qubit gates, then you can do just log 1 epsilon many T gates. And for mass production, if you want to implement m copies of the same single qubit gate, then it's m plus an additive log 1 epsilon. So these are the main results. And now I will talk about some open problem. The first thing is about stabilizer rank. So one way to implement the T gate is to use gate injection so that you don't actually need T gates afterwards. So if you are given this magic state T, it's actually called magic state. Okay, it's not something it's not an adjective.
Lynn Kataev.
Yes. And like physicists, they use fancy names. This state is called magic state. And if you want to implement the T gate, you can assume, if you are given this state, then you can implement the T gate without Clifford operation. And the way you do this is to first do a C naught, and then you measure the second wire, and based on whether it's 0 or 1, and this is a classical information, you apply the phase gate or not. So this is something simple. And if you take it for granted, then you can actually have this conversion. So assume you have like Clifford plus T circuit with m T gates, then it actually can be executed with m copies of magic state followed by Clifford operations. So kind of we converted from Clifford plus T circuit to a Clifford circuit. But the caveat is we need this additional resource. And recall that we know the Boltzmann-Knell theorem. It says Clifford circuit starting with O0 is classically simulatable. So if we can decompose this tensor product of magic state into something like Clifford operates on like inputting O0, then we can apply Boltzmann-Knell theorem to get a simulation of these circuits. So this is the statement. If there are Clifford circuits, C1 up to some like CR, and there are some coefficients, such that this special state can be written as linear combination of this Clifford circuit acting on O0, then the original circuit can be classically simulated in time Rm times poly m. The reason is you just, well, the Clifford circuit acting on like T tensor m is the same as Clifford circuit acting on this CK time operated on O0. And then this will be poly m time. And then you aggregate them because this is linear, so you propagate. And why is called stabilizer rank? Well, these states are called stabilizer states, and this R is a stabilizer rank. And because because we believe that we can't simulate like BQP algorithm with polynomial time algorithm, even with like non-uniform advice, this Rm shouldn't be a polynomial. Right? Because if Rm is a polynomial, like poly m, then m is going to be poly n. Every BQP algorithm will just use poly m and T gates, and the simulation will be too efficient to be true. So, so this raises the following conjecture about stabilizer rank. It just says if you can write the m tensors of magic states into linear combination of stabilizer states, then this linear combination should involve exponential many stabilizer states. Otherwise, you get a very efficient simulation of BQP algorithms. And if this conjecture is true, then it will imply, at least for this, like using Boltzmann-Knell algorithm, you cannot like show that BQP was B. So this is some like conditional ruling out a class of algorithm. And for this question, there has been some work. So first, there is a trivial upper bound 2 to the m of this rank. And it turns out you can do something more efficient. So you can do like 2 to the 0.23 m. And somehow this improvement comes from similarly analyzing like decomposition of tensors, just like matrix multiplication. Like you don't always need like n-qubit time. You can do something more efficient. And this is the same thing happening here. In terms of lower bounds, the first lower bound was square root m, and then it was improved to linear by like 3 works using 3 different techniques. And recently, there's a work proving an almost quadratic lower bound. And this work uses the state preparation algorithm as a black box. Because the state preparation has a square root saving that translates to the square lower bound here. So that's very, very high level, like why it has square here. And that's because we have a square root saving in the state preparation case. And because we improve the state preparation, we can shape some logs. So the log to the 4 is improved to log to the 2. And this log to the 2 comes from a union bound that is independent of the state preparation task. Okay. And why do I mention this, this problem? Is because it's related to Boolean functions. So this is a function called quadratic uncertainty. Let f be a Boolean function that maps 0, 1 hypercube to 0, 1 output. And suppose we have linear functions L1 up to Ls, and coefficients A1 up to As, such that you can write fx as a linear combination of these linear functions. So it's sum of AK times minus 1 to the LK. And the question is, how sparse this representation can be? What is S? And because we all know Boolean functions, we know this minus 1 to the linear is just the parity, like the Fourier basis. So this is actually a unique decomposition. So SF is just the minimum number of non-zero Fourier coefficients of F. So nothing is interesting here. And things becomes interesting when you replace the linear functions with quadratic functions. So now we have quadratic functions Q1, Q2 up to Qt, and we still have those coefficients A1 up to AT. And we want to write F in terms of the linear combination of these quadratic functions. So it's sum of AK minus 1 to the QK. And now the question is, again, how sparse this can be. What is T of F? And because we incorporated quadratic functions, so this is more than a basis. So every function has plenty of other ways to write it. So we'll care about the sparsest among them. For this function, surprisingly, even for simple function like AND, we don't know the answer. So this is a conjecture by Haim Tatami, who was here but not here anymore. I'm a bit sad. Okay, he asked it like 13 years ago. What is the sparsity for AND function? And he conjectures it should be exponential, just like you expand it in the Fourier basis, that every Fourier coefficient is non-zero. And he conjectures even if you put in quadratic functions, it's going to be like expansion. But unfortunately, we only know a linear lower bound. So this is pretty sad. And now people ask, okay, we can't even know like, this function. What about other functions? What about explicit function in reasonable computational class? And this was studied by Ron Williams and and a follow-up work with Lydia Chen. They show that for any fixed number k, there exists a function fk in MP such that the sparsity is at least n to the k. Okay. So they use some algorithmic method to show this. And what about the functions in P? And this comes from this recent improvement on the stabilizer rank I just mentioned by Miraba, Tomasky, I'm not sure if I pronounced it correct. Anyway, they show that the near quadratic lower bound in their stabilizer rank thing translates here. So there exists a function f that's in P has roughly n square sparsity, even you allow quadratic phases. And interestingly, this f is just simple. It's a Hamming-weight mod 8 function. So you input x, you take a look at its Hamming-weight. If it's equal to 0 mod 8, you output 1, and otherwise output 0. So this is a symmetric function, and that's pretty simple. And it has a near quadratic lower bound.
So there are no explicit function that you know the lower bound is 2 to the n?
No. We know it's 2 to the n for random function. That thing you can prove. But we don't know for any explicit function. And because of that, that's a black box reduction. We also shave the polygon. And why, like the stabilizer rank stuff has something to do with this thing. So first, it's like most of the questions talk about linear combination of things. So this is one common part. And in the stabilizer rank thing, these quadratic phases are stabilizer states. And here it's quadratic functions. And turns out these two are very similar, as you probably saw from Srini's talk. So quadratic polynomials are like Clifford circuits, so that the lower bound there would translate to the lower bound here. But it doesn't prove for any function. It's proof for this mod 8 function. So this lower bound improvement doesn't imply improved lower bound for AND. And we hope maybe like techniques improving this one here can be used to improve like the stabilizer rank problem as well. So it's kind of a sibling problem. And also, because this goes through that stabilizer rank, Clifford circuit, all those quantum maths, it's a quantum proof. And this is a classical statement. And my natural question is, do we really need quantum to achieve such a proof? Okay, so this is the part about like very explicit about Boolean function. And next, I will talk about, and also this problem somewhat is known in the literature. Like they have a fancy name, quadratic uncertainty, and also stabilizer rank lower bound. That's a fancy name. And next, I will present somewhat less known problem, and hopefully maybe you have some insight about it. And this is a problem proposed by Dominique Barry. Actually, this is a problem that got me into this project. And we couldn't prove it. We found some way to bypass it, but still it's going to be, it's very interesting. So we know that if you can implement a diagonal unitary, then you can at least correct the phase of the amplitude, because diagonal unitary just corrects the phase. And the question is, how many diagonal unitaries will be able to construct the state? So correcting the phase is like making some progress. Right? At least you make some progress. And the question is, how many diagonal unitaries you can complete the progress? So in particular, he conjectures the following circuit will be sufficient to construct any state. So you start with all zeros and apply a layer of hard mod, and then apply a diagonal unitary, another layer of hard mod, another diagonal unitary, another layer of hard mod, and a final diagonal unitary. And that's it. You can implement any state without any error. So all the choice comes from how to cleverly pick D1, D2, D3. So if you are given a state psi, there exists diagonal unitaries D1, D2, D3, such that the above circuit will construct your target psi. This is his conjecture, and he even implemented some algorithms, heuristic algorithms, try to verify it up to, I think, like 26 qubits. But that's numerical. So his algorithm goes as follows. You initialize some random D1, D2, D3. I don't know what that is. We initialize it. And then we fix maybe D1 and D2, and choose the optimal D3 to be close to psi as possible. So we constrain D3 to be diagonal unitary, and then we optimize it so that it's as close to your target psi as possible. And then we fix D3. And then we fix D1, D3, and optimize over the best D2. And then we fix D2, D3, and optimize over D1, and you iterate this. And his algorithm finds that for random inputs, it always converges to the target psi. So this is his algorithm. And why this is the structure, like why we care about this structure, why he asked in the first place. First is simple. You have diagonal unitaries, and what's the simplest Clifford operation? Well, hard mod, you just take the Fourier transform. And also it captures correlation, which is PQP complete. In correlation, we have Hadamard, Boolean oracle, Hadamard, Boolean oracle, Hadamard, Boolean oracles. Keep doing this. So at least this circuit, if you allow about like many diagonal unitaries, it will complete all the computation in PQP. So this is kind of a universal circuit. And third, it's easy to analyze the cost, because we know what's the cost to implement a diagonal unitary, and Hadamard is free.
Sorry, I just asked about BQP completeness. Can you restrict the values on D?
So to get BQP completeness, you can even use Boolean diagonal unitary. But here, because of discrete issue, like discreteness, if you use Boolean, then it will never be true.
Oh, right, because a TOEFL plus H is BQP complete. Okay.
Yeah,
Okay.
yeah.
Got it.
So it's kind of like this kind of circuit appears in other equations. So it's kind of also natural on its own.
Yeah.
So these are the like three main reasons why we look at this. Okay, is this clear? Okay, cool. And now let's see what it implies. Okay, if this conjecture is true, then we can combine it with the diagonal unitary T count we had before. Each one of them just needs this number of T gates. So in total, you just need this many T gates. You just implement diagonal unitary itself. And that's optimal because we have lower bounds. And this is a much simpler proof and more direct, right? Just a structural lemma combined with diagonal unitary seems the result. And also the constant is better because if they care about like classical implementation. Okay. And we did some study on this problem, and let me show you what we can get, or some just simple observation. So let's first look at what if we only have one diagonal? What can we produce? Like why 3, right? So the observation is it's just going to be a phase state. So a state psi is obtainable in this one Hadamard, one diagonal structure, if and only if all the amplitudes are having like norm 2 to the minus n over 2. Why is that? Because well, all 0 is mapped to the like uniform superposition state after this Fourier transform, and then you apply the phase on it. So it's got to be like this. Okay. So that certainly we know it can't generate all the states. So now what about 2? We have another layer. And it turns out the states can be obtained in this structure if and only if it's a Fourier distribution state. So you take the amplitudes and square it, that's going to be a distribution. And if this distribution corresponds to the Fourier distribution of a complex Boolean function, then you can implement it. Okay, so what is a complex Boolean function? It's a map from hypercube to complex number, unit complex number. And what's the Fourier distribution? Well, you have a Boolean function, so you can talk about the Fourier transform. You have Fourier coefficients, you square them, and this is going to be the Fourier distribution. So, so we know not every distribution is a Fourier distribution, so certainly this is not complete. You can't generate all the all the states with 2 diagonals. And the proof is pretty simple. You just decompose d1 into the like Fourier basis. Like this d1 is computational basis, but you decompose it and you can get this. This is if and only if.
It's if and only if.
Yes, it's if and only if. Yes. And because of this, for example, let me just mention a few things. Because we have this characterization, you can show, for example, the stabilizer states are obtainable with 2, because stabilizer states are uniform over subspace, and subspace is something you can construct a Boolean function to just support on that subspace. So this is sufficient for stabilizer states. Okay, so 2 diagonals is also not sufficient. What about 3? And the thing is, it becomes more complicated, but still I feel it's like a Boolean function problem, because the previous one is a Fourier distribution, try to give some structural result on the Fourier distribution, and here it's similar. So every state is obtainable if and only if any distribution. So this is arbitrary distribution, and we want to convert it into Fourier distribution. That's special distribution. And how we are going to do this? We will apply a complex Hadamard transform. That's a complex Fourier transform. So Fourier transform is just the Hadamard gates. And what's complex Hadamard, like complex Fourier transform? It's adding like faces, adding faces on the left and the right. So you choose this complex,
prime means
different.
just
A different one. It's not conjugate. No,
Oh,
just different.
one.
Different. Yes. Yeah, that's different. Yeah. So you don't work with the standard Fourier transform. You use a complex, you use a complex form of this Fourier transform, and after this, it will become a Fourier distribution. So his conjecture will be true if this thing is true. Every distribution will be converted into Fourier distribution by a complex Hadamard transform. And this is something we don't quite expect from classical, like if the output is just binary. And we also talk about Fourier distribution. And there is no like structural lemma you can show for that, because it's discrete and you can't use like finite number of things to approximate it. But for continuous case, this is the conjecture. Somehow, if this is true, then it gives also a structural lemma for what is a Fourier distribution for complex Boolean functions. Well, it will be any distribution after you properly change your basis of the Fourier transform.
Kevin, can you write example of complex Hadamard?
Yes. So the Hadamard is like 1, 1, 1, minus 1, and times 1 over square root 2. And then we can apply like different things. Maybe here is I, here is yeah, I think that's write it 1 e to I theta 1, and another diagonal entry 1 e to the I alpha. And then you can compute what's it.
Yeah, okay.
So it's like square root 2.
Yeah, but it shouldn't be 1, right? It can be.
Oh yeah, it can be anything. Like e to the I theta 1, theta 2, e to the I alpha 1, alpha 2. And
No, it's okay.
But so this is happening on each qubit independently?
no,
In general.
in general. So in general, it will be
So it's not a 2 by 2 Hadamard, it's a
yeah, it's
2n by 2n
H-
Hadamard matrix.
tensor n, and then you can design some d and let's say d1 H tensor n and d2.
Right. And there's no tensor structure?
No tensor structure in d.
Oh, no
Yeah, because we
tensor.
can afford to construct those.
So diagonal without e to the.
Yeah, it's no tensor structure.
It's false. It's tensor structure.
Yeah, I think it will be false. It's tensor structure. Yeah. Okay. For this conjecture, we know how to prove what n equals 1. Single qubit case. And for n equals 2, we already don't know how to do it. So we don't know how to prove for the n equals 2 case. And we did some other attempts, like try to use some convergent argument to analyze his algorithm, because I mentioned there is an iterative algorithm try to converge to the side. And it turns out not every initialization would work. So he used random state and also random initialization, and we could show that there exist states and exist initializations that his algorithm doesn't work. So somehow this is randomization helps in his experiments.
And it's
But
one,
sorry.
okay, no, you go ahead.
But for the previous two states, it is true, right?
Oh, you mean one diagonal and two diagonals?
Yes.
Oh, those we give like tight characterization.
Okay.
Yeah, so yeah, this is fact.
Okay.
This is proven. Yes. And when you have one more, we suddenly don't know what to do.
Right. So it's much harder to show that it's non-zero probability that the initialization works.
Yeah, that will be a harder statement. So
And
this,
you would imply that.
yeah, let me maybe mention a few things, because it seems that you want to discuss about this problem instead of reading the proof. Okay, so his algorithm looks like this matrix balancing problem, in the literature where you have a any matrix can be if you multiply by some diagonal on the left and a diagonal on the right, you can make it like a stochastic matrix. This is a result called, I think it's called single-qubit theorem. Like any matrix, you can balance like times some diagonal unitary and another diagonal matrix and another diagonal matrix. You can make it a stochastic matrix. And there are proofs using like algorithms, like iterative algorithm looks like that. You fix one and you optimize the second, and you fix the second, you optimize one, and there is a analysis showing this converges, and we'll try to mimic that algorithm, the proof of that, and it doesn't work. Yeah. So right. So anyway, this is the conjecture and some study we made, and to be honest, this. If true, will be the best, but even if it's not true, like you can replace like 3 with some other constant or some other factor, that will be perfect. All we know is when we increase 3 to 2 to the n, it's true.
Mm-hmm.
We don't even know whether it's true for poly n or something.
I think it should be for poly n by state synthesis. Or by Rosenthal, for example.
That will incur ancillary qubits.
It will what?
That will need ancillary qubits.
Oh, is that that's the difference?
Yeah. So here we don't want to use ancillary qubits.
Oh, so if you do allow ancillary qubits?
Yeah, I think you can use, that will be poly n, because Rosenthal has a paper showing you can use QAC0 with one query oracle, Boolean oracle, and you can synthesize the state. Yeah, that is true. But we don't want to use ancillary qubits. Okay, so this is conjecture, and should I talk about proofs, or we should just let everyone go along?
Completely up to what people want.
Okay, maybe let me just say like why it's square root. Okay, that's like why you expect this square root thing. Okay. So there are 2 proofs. One is diagonal unitary and one is state preparation. And the full slides is on my homepage. So if you are interested, you can go check it. And also we have the paper. So for the diagonal unitary, I will explain what is this. Why do you have square root theory? And the state preparation circuit is like the algorithm is developed by Rosenthal, and we just analyze in our setting with some tweak. So right. So this is a statement for diagonal unitary, and let's take a look at the Boolean diagonal case. So assume you have a Boolean diagonal unitary that has +1, -1 entries. What is the cost to implement it? And this is square root 2 to the n. And because of this, you can reasonably believe, even if you have like complex numbers, it should still like square root 2 to the n, maybe ignoring those log 1 epsilon stuff. Okay, so let me just explain like why this thing is true. And this is true because of a classical reason. Any Boolean function has a Boolean circuit that only use AND gate and parity gate. And the number of AND gate is square root 2 to the n. And we don't count the number of parity gates. So this looks somewhat like Shannon's circuit bound, but here we have square root 2 to the n instead of 2 to the n over little n. And then, if you accept this, every AND gate is a Toffoli gate in quantum computing.
Sorry, this is like NC1 or AC, or like NC or AC?
Constant fanning.
Constant fanning.
Yes. So it's a constant fanning circuit, so every gate has 2 inputs. Yeah. So the AND gate corresponds to Toffoli gates in quantum computing, which can be constructed using T gates. And parity gates is C0 gate, which is Clifford, that we don't care. So this gives the square root 2 to the n. And why this is square root 2 to the n? Well, actually the proof is very similar to Shannon's bound, where you kind of do a trade-off. You expand the first few bits, and then after a certain amount, you write out all the circuits on the rest of the bits. And it's just choosing a different trade-off will give you this, because we only care about AND gates, not parity gates. So this trade-off will give you square root of 10. And this complexity actually has a name. It's called multiplicative complexity. So it's talking about how many multiplications do you need in your classical circuit. Because AND gate is like multiplication, and parity is like just linear combination. And this multiplicative complexity was studied like way before this quantum circuit problem. And it was also used in crypto. Somehow there, the AND gates are also more costly. So this is like why we have a square root thing. Okay, let me just stop here and everyone can have lunch.